Good afternoon. Good afternoon, colleagues. My name is Jan Yusupov. Today we will consider and discuss geomechanical problems on example of 1D geomechanical model. Among the tasks for webinars is using, for example, of 1D geomechanical model in Litho Studio software for decision of next tasks. Among them, evaluation of the safe mud weight window, including well-bore instability intervals, abnormal reservoir pressure, mud losses, etc. So drilling problem prediction as blowouts, stickings, collapsing, overpulls, landing, etc. We'll design optimization and correction of casing shoes, depths, landing. At last, this is optimal direction and angle of drilling determination. Okay, this is a typical geomechanical model workflow that we will consider in this webinar. The first step of geomechanical model building, this is calculation of elastic and strength properties model, total vertical stress based on density logs. This is step number 2. Step number 3 is pore pressure calculation. It's calibration of fact data as MDT, XPT, etc. Near wellbore stress state, including horizontal stresses calculation and calibration of borehole stability model. This is step number 5. And final step, step number 6, this is interpretation of calculations, borehole stability well section building, drilling optimization recommendation, and another tasks. Okay, let's start. Litho Studio software, this is one-dimensional modeling geomechanical simulator that developed by our team. We developed this software from 2015. This is very simple software. In upper part, this is chronologically masters. This is project, including all functionality that allows to import, export data. Among this data, this is logging, tables, core data, stratigraphy, lithology, tops, saturation, casing, drilling events, well testing data, mud weight, and another input data. The tab number 2, this is data tab. This tab includes statistics, cross plots, histograms, interval correlations, Python scripts editor, formula catalog, data smoothing data, converter, log audit, and recycle bin. Petrophysics tab, this is a tab that allows calculate all necessary petrophysics data for 1D geomechanical model, among them shale index, porosity, permeability, bulk density, P wave slowness, S wave slowness. The next tab is geomechanics. This is main tab in this simulator. This includes chronological sequence of geomechanical masters from the simplest master. This is mechanical phases, dynamic elastic properties, static properties, and 2 scenarios and workflow. We will consider this sequence in this webinar. The next step, this is well section. Well section includes settings for visualization on the well section. And last tab is settings of project. Okay, let's start. Consider 1D geomechanical model on example one of well. This step number 1, calculation and calibration of elastic and strength properties model. Okay. To calculate elastic and strength properties profiles, we need etc. We need P wave slowness, we need S wave slowness, bulk density, caliper, only DTP, DTS, and density. All data that you can see in the tree-like structure can be moved on the well section, but if we want make it very quickly, we can use the templates. Okay, these templates show us all necessary input data for calculation of mechanical properties. This is P wave and S wave slowness calibrated on core data, bulk density, gamma ray, caliper, and mud weight, input mud weight. Let's add on this well section tops, stratigraphy, and lithology. Okay. So let's go to the next step. Step with calculation of mechanical properties. To calculate mechanical properties, we need use master dynamic elastic properties that will used for calculation of dynamic Young modulus and dynamic Poisson ratio. Both both parameters includes in dynamic elastic properties. At first, we need select curves, P wave, S wave, and bulk density for calculation of dynamic Young modulus, and P wave and S wave for calculation dynamic Poisson ratio. Okay. After this selection, I should press run, and this curve will be in tree-like structure. Let's move it necessary folder. MEM, this is mechanic Earth model. Okay. We calculated dynamic elastic properties. After this, let's calculate static elastic properties. For calculation of static elastic properties, I should open the master static properties. If you can see here, we will use different correlation for different layers. For example, in this case, we will use free empirical correlation for 3 layers, for 2 layers, I'm sorry, and another correlation will be used for all cross section. Okay. Run the static Young modulus and static Poisson ratio was calculated. Okay. Let's open this curves on the will section. Let's try correlate log data with core data. Okay. Sorry, I forget to check input data. Okay. Please note, after checking input data, this interval of curve will be changed. Okay. Dynamic. Okay, good. If you can see here, the core data is very good correlated with logging data. After this, we can go to the next step. The next step is calculation of strength properties. Among stress properties, we can highlight unconfined compressive strengths, unconfined tensile strengths, and friction angle. All these parameters can be calculated by empirical correlation. And for this correlation, we need to open the master strength properties. This master includes tensile strengths, fixed cylinder wall test, uniaxial compressive strengths, internal friction angle. At first, let's calculate uniaxial compressive strengths. We will use two empirical correlation for one stratigraphy, and for another cross-section, we will use second empirical correlation. Okay, let's run. Let's open the UCS on the wall section, and we will correlate and check UCS with core data. If you can see here, the core data of UCS have good correlation between with UCS by logging. Okay. The step number, next step, this is friction angle calculation. Let's use for friction angle correlation, LAL correlation. Run. And let's check friction angle and correlate this with core data. This is not wonderful correlation, but this is satisfaction. Okay. Next curve is TSTR, tensile strength. Tensile strength. This is uniaxial tensile test for calibration. We'll use here, and we will use here user formula 0.2 multiply UCS. Run. Good. Let's move the core data and check the results of calculation of TSTR. Okay. We finished the step number 1, calculation and calibration of elastic and strength properties model. Let's use template for mechanical properties. And rename this template as well section 2 mech properties, mech props. Okay. Okay. Step number 2. Let's go to step number 2. This is total vertical stress based on density logs. Let's consider input data and process of calculation of total vertical stress. In our project, density log will not recording at the shallow depths. So in this case, we will use empirical method that can be used to estimate shallow formation bulk density by Traugott method. In this case, we have onshore well, so offshore will not used. And in onshore well, we will consider only calibration and rocks bulk density. We will not use water depths. Okay, let's calculate overburden gradient. To calculate overburden gradient, we must open the master overburden gradient, select the necessary bulk density curve, check rotary table, check synthetic bulk density equation, and select kind of resulting data. We will select a gradient, overburden gradient, and result density. Okay, run. Okay, if you can see here in tree-like structure, we see two parameters: full density. Full density implies synthetic density in shallow depths plus bulk density in main depths. And let's move it into stress folder. Okay. Let's check and let's use templates to open the overburden parameters on well section. Okay. Please note that the track number 1, the highlight curve, this is original density curve. The pink curve, pink density curve, this is original curve plus synthetic and calibration. OBG, this is overburden gradient that calculated from density, full density. Okay. This was step number 2, total vertical stress based on density log. The calculation of total vertical stress is most easiest step in calculation of 1D geomechanical model. Let's go to the step number 3, pore pressure calculation. Let's close the well section with overburden stress and go on pore pressure calculation. To calculate pore pressure, we must at first create the borderline in the gamma ray curve. Left, we will see sands, and right, place. After this, we will show the shale line gamma ray on the well section. To not lose time, I have already prepared this borderline, and let's check it into the well section. Okay. Let's fill space between borderline and gamma ray. Okay. The space on left part, this is sense. Texture. Send. The space between shale line and gamma ray on right part, this is Claise. The pore pressure estimation will calculate it only inter-shale intervals, because Eaton methods works only for shales, only for clays, but it doesn't work for sandstones. Okay. After this, we must create the shale points and shale line datasets. To create these datasets, we must use master for creation of shale line and shale points. For this, we must select shale identification borderline curve, gamma ray, base curve for Eaton methods, p-wave slowness, and borderline, shale line gap. Run. Good. We calculated this data sets. Okay. After this, we must calculate the normal compaction trend line. To calculate normal compaction trend line, let's use master normal compaction trend line and select base curve for compaction trend line. This is shale line. Okay. For normal compaction trend line, let's select square and run. Okay. And let's change the fill for normal compaction trend line. And let's change the type of scales. Let's use inverse scale. Okay, this is normal compaction trend line. This is parameter that used in Eaton equation. Let's go to the calculation of pore pressure gradient by Eaton methods. Okay. To calculate pore pressure gradient by Eaton methods, we should use the pore pressure gradient master pore pressure. We should select overburden gradient, hydrostatic pressure, normal compaction trend line, and shale line by DT. Okay. Eaton. Okay. Yes. We calculated pore pressure gradient by Eaton. And let's check the results. To calibrate pore pressure gradient, we must use the pore pressure data. Pore pressure data, and check the pore pressure profile. Okay. Let's use smooth pore pressure profile. Because it is more have more physical sense. Please note that at first we calculated by Eaton pore pressure gradient in shales from logging. After this, we smoothed this calibration, this pore pressure profile, and calibrate this smooth profile on PPG data, MDT data in sandstones. And for next work of this work, we will use PPGDF, smooth profile of pore pressure gradient. Okay. Let's close this that we all have already calculated, and let's go to the step number 4. This is near wellbore stress strain state. This step includes calculation of minimum and maximum horizontal stress gradients. Before start calculation of horizontal stresses, let's use template. Let's apply template to visualization of pore pressure gradient. Okay. This is typical example of visualization of pore pressure. This is stratigraphy, lithology, shale line, normal compaction trend line, and calibrated pore pressure gradient profile. Okay. To calculate minimum and maximum horizontal stress, let's open the master horizontal stresses. To calculate horizontal stresses, we must use pore elastic model. In this case, overburden gradient. This model includes overburden gradient, pore pressure gradient, Young modulus, static Young modulus, Poisson ratio. In this case, we will use Poisson ratio static equal Poisson ratio dynamic. That this is in this calculation, we can use Poisson ratio dynamic. Biot pore elastic coefficient, by default, this coefficient equal 1 because we have not core data for calibration of Biot pore elastic constant. Epsilon H big and epsilon H small. For SH max, we have the same parameters. Okay, let's check the names of curves. SHG, this is minimum horizontal stress gradient, and SH max G, gradient of maximum horizontal stress. Okay, run. After this moment, let's move this into stresses. Let's visualize. Let's show the minimum and maximum horizontal stress on the well section. Horizontal stresses. Let's use the template Number 5, horizontal stresses. Okay. On this well section, they showed the profiles, combined profiles of pore pressure gradients. Pore pressure, input static mud weight, minimum and maximum horizontal stresses, and overburden gradient. Okay. Let's save the well section and go to the next step. Next step is calculation and calibration of borehole stability model. Borehole stability model includes calculation of shear failure gradients and tensile failure gradients, SVG and breakdown gradient. This calculation includes Kirsch solution. This solution can be realized as for full depths of well. Also, it can be realized in a 2D solution around well section. For example, we can calculate the distribution of stresses around the well for any depths, and we can check the depths. We can calculate these parameters. For example, we should check the distribution of stress in this depths. After I can move the cursor and calculate the radial stress, hoop stress, axial stress, shear failure gradient by Moore-Coulomb, shear failure gradient by Lade, breakdown gradient. These parameters can be calculated and visualized as radial distance, as well bore well, and as for stereo nets. Okay. Let's calculate shear failure gradient and tensile failure gradient and open the master shear failure formation breakout analysis. To calculate from shear failure gradient, we must select OBG, PPG, elastic and strength properties, and azimuth of SH max. Okay, after this, we must we must run the calculation. After this, we will get profile of shear failure gradient and imager of shear failure gradient. Imager drawed only intervals where shear failure gradient are more than static mud weight. For example, let's fill the intervals between mud weight and shear failure gradient. On the right part. Okay. The intervals where we see shear failure gradient more than mud weight static. This is we we consider that these intervals are breakouts. Let's check this and compare this with caliper data. For this, let's use well section Warhol stability and apply the VHS template. Okay. Okay. Please note that this well section, the first track is stratigraphy, lithology, casing, caliper, wireline, and combined pore pressure gradients. To compare the shear failure gradient distribution in the well section, we should compare this profile with caliper. We see that the interval of caliper, these intervals of Km and above Kz, there are breakouts. This is this situation also observed in the FR formation. Okay. To change the distribution of breakouts, let's recalculate curve, and we will use in this interval coefficients to recalculate shear failure gradient. Okay, after this, we see that the distribution of shear failure gradient is more better to compare this caliper. Sorry. Okay. Good. After we calculate the shear failure gradient distribution, we must calculate breakout gradient. Breakout gradient, this is tensile failure parameter gradient. To calculate this parameter, let's open the breakout gradient master. To calculate breakout gradient, we should have overburden gradient or total vertical stress pore pressure gradient, SH max, SH min, azimuth of SH max, Poisson ratio, BO poroelastic coefficients, and TSTR. Yes, wrong. Let's visualize the breakout gradient on the well section. Okay, let's check. We see in this well section yellow points and pink points. The yellow points, this is fracture closure pressure. Fracture closure pressure by definition is equal minimum horizontal stress gradient, and the yellow points fracture closure pressure can be used for calibration of total minimum horizontal stresses and minimum horizontal stress gradient. Without difference, but in this case we use only gradients. Also, the pink points means breakdown gradient. Breakdown gradient, this is pressure. This is pressure value when we see full breakdown into the layer. This point these points can be used for calibration of breakdown pressure and breakdown gradient. Okay. After this, we can remove the SVG and PG in folder and build the final well section and called it as mud weight window. And mud weight window. Okay. This is a final plot of a 1D geomechanical model. It's called as combined pore pressure gradient. This is step number 6. On base of this plot, this well section, we will make the drilling optimization recommendations, recommendations for casing shoes depths, etc. Let's discuss the combined pore pressure gradients well section. On this plot, we see the different fields. The gray fields, this is zone of pore pressure. If we use the mud weight in this zone less than pore pressure, we will observe the blowouts, gas shows, oil shows, and another troubles. The yellow filling is zone of shear failures. If we use mud weight less than shear failure gradient, we will observe the cuttings, the cavings, the increasing increasing amount of cavings, stickings, landings, and another drilling events. The correction of calculation of shear failure gradients confirmed by compared of shear failure gradient profile and caliper wire line. Yes. As we can see on the caliper, we see the breakouts, and we see the breakouts in this casing, in this interval of wells 2. Okay. The white zone, this is a safe mud weight window. The blue zone, this is losses zone. If the mud weight static will be more than SH mean, total minimum horizontal stress gradient, there will be reactivation already existed faults or fractures. If there are no existed faults or fractures, their excess of mud weight then total minimum horizontal stress will not lead to the losses. But if we across the mud weight more than breakdown gradient, this is dark blue zone, this is will observe full breakdown, and we will get the losses. This will be very bad for drilling history. Okay. If you can see here, the profiles of total minimum horizontal stress gradient and breakdown gradient calibrated on the XLOT and Minifrax stress tests. Also, we can use for estimation of drilling sensitivity, the stereo nets. Stereo nets shows the dependence of shear failure gradient to angle and azimuth of wells. For example, we must select the depths, interesting depths, and calculate the StereoNet. The StereoNet shows how shear failure gradient, so this parameter, yellow parameter, depends on azimuth and angle of well. In this case, in case of normal fault, the most stability interval in terms of drilling will be vertical well, and the most instability interval will be direction of maximum horizontal stress, horizontal well in the direction of maximum horizontal stress. Also, we can calculate the breakdown gradient distribution and dependence of breakdown distribution on azimuth and angle of well. So, okay, let's check. The how shear failure gradient will be changed if we will use another stress regime. For example, let's use multiply coefficients for SHMax. After this, after we used the multiplication coefficients K for SHMax, we change the stress regime from normal fault to strike slip. In the strike slip, the most instability interval will be vertical well. The most stability interval will be horizontal well drilled by direction of minimum horizontal stress. Also for breakdown. Okay. Also, we can check the situation for reverse fault. For example, let's increase the SH min to 2.1 and another parameter by default. Okay. As for thrust fault, the most instability interval by thrust fault will be horizontal stress drilled into the direction of minimum horizontal stress. Okay. After this, let's discuss the problems that was shown into the presentation. Okay, we considered the wellbore stability well section, wellbore stability plane. Let's go to the drilling optimization recommendations. For this case, we can change the casing. We can change the casing because we see the dangerous intervals in this well. For example, let's draw the project mud weight window curve. For example, to new casing recommendation casing. This is, for example, first interval will be use mod weight static more than shear failure gradient by Morculon. Moment. Yes, mod weight recommendation. Okay. For example, 1.25 1.25 gram per cubic centimeter. After this, we should increase the mod weight static, because in this interval very dangerous in terms of tides, landings, and increasing of cuttings. I think this will be more mod weight static. Yes, I think this will be more. Yes. After this, we go to the reservoir part, and we must decrease the pore pressure or mod weight density. Okay. Because this interval is unpermeable, in this interval, using of mod weight less than pore pressure gradient will not lead to the blowouts. Okay. On this example, we optimized the mod weight for future well after analyzing of distribution of combined pore pressure gradients and accounting the problem intervals. Okay, let's go to the next problem. This is recommendations for hydraulic fracturing optimization will not consider in this webinar. So the recommendation for casing depths we will consider, have already considered, and recommendation for reducing model uncertainties, well logging, core studies, stress tests. Okay, to accounting the uncertainties, we will use master sensitivity analysis. This master can build the tornado plots and spider plots to sign the parameters that have most influence on calculation of shear failure gradient and breakdown gradient. Let's check. Let's use any interval, for example, most problem interval in the bottom of phi r layer. Okay, let's select the parameters that we used for calculation of shear failure gradient. This is azimuth of SH max, horizontal stresses, pore pressure, overburden gradient, strengths, and elastic properties. After this, calculate the tornado plot. Yeah. After the calculation of tornado plot and spider plot, yes, we see the most significant influence this is makes the SH max gradient, pore pressure gradient, BO for elastic model, and total minimum horizontal stress gradient. This is assessment of uncertainty, shows that we should make the uncertainty of this parameter, we should make uncertainty of these parameters less, because they have a big influence on the correct calculation of shear failure gradient. Also, let's make estimation of uncertainties for breakdown for this curve, for breakdown gradient. Okay, we will switch off the breakout and switch on breakdown. After this, calculate the tornado plot, and let's see. If you can see here, the most influence makes the total minimum horizontal stress, maximum horizontal stress, and pore pressure. If we as for SH mean and pore pressure gradient, we know these parameters very well, and we can use the uncertainties of these parameters as here in this model. But as for SH max, this parameter have very big borders of uncertainties, because its parameter cannot calibrate it rightly on any tests or any investigation in wells. So as for conclusion on this uncertainty analysis, the SH max is very dangerous uncertainty parameter, and we must control this parameter to correct calculation, shear failure gradient, and breakout gradient. Okay. We consider the calculation of 1D geomechanical model. We consider uncertainty parameters and control by uncertainty parameter. After this, let's go to problems of sand production. And in our software, there are two models for sand production. This is qualitative sand production for all well section, for all well, and quantitative sand production. Okay. Step number one, this is qualitative analysis. To use the sand production master, we should transfer the total stress gradients to total stresses, because this master uses only total stresses. Okay. Let's save the project. After this, we will use the converter. Converter will allow to transfer gradient to pressures. At first, this is breakdown gradient to fracture breakdown pressure, gradient to breakdown pressure. Run. After this, OBG, overburden gradient to overburden pressure. Run. PPG to PP, pore pressures SVG to SVP, shear failure gradient to shear failure pressures, and SH min and SH max. SH min and SH max. Okay. Let's visualize these parameters on new well section. OBP, SH min, SH max. Okay. And change the color for OBG. Okay. Okay. After this, let's return to for send prediction modulus. To make calculation in send prediction modulus, we at first we must select the interval to estimation send production. For this, I need the stratigraphy, lithology, and parameters of mechanical elastic properties. Static Young modulus, Poisson ratio, and UCS. Okay. For example, let's make calculation for this interval from 2310 to 2340. 2310 to 2340. Okay. I forget to set the input table with for pressure to visualize the steps on the triangle. Sorry. Okay, let's use the send production for all well. For calculate the send production for all well, let's open the send production master and select the parameters: overburden pressure, pore pressure, SH max, SH min, UCS, TVS, and calibrated parameters. After this, we will select as for result data, critical drawdown pressure, critical bottom hole flowing pressure, 2 parameters, and run. For example, also we can use using lithology to calculate these parameters only for definite lithology. For example, this only for sandstones. Okay, let's check. For checking the calculation of these parameters, A moment. Check. Okay. After calculation, we calculate the critical bottom hole pressure to avoid sand production. This is curve. This is pore pressure, red, green curve, and violet curve. This is critical bottom hole pore pressure that necessary to avoid the sand production. Okay. Uh, okay. Now let's finalize the results of this seminar. In this seminar, we use the 1D geomechanical model built in Alito Studio software for evaluation of the safe mud weight window, including borehole stability intervals. We consider drilling problem predictions as for in terms of oil and gas showing, blowouts, stickings, collapsing, sand production, overpulls, landings, etc. Also, we changed the well design, optimized and corrected the casing shoes depth landing, and we consider the optimal direction and angle of drilling determination. Okay, thank you so much. I think that is